Good morning, good afternoon, good evening, whatever the case may be. We are back and better than ever. Who is she that's been on my mind forever? Well, she, of course, is calculus. And we are at optimization part 4. And just one example that we need to do here in this video. It's a winner of an example. So, two corridors. Corridors are hallways, yes. So we have a hallway here and a hallway here. Meet at right angles. So we are at a right angle here. And are 2 meters wide and 3 meters wide, respectively. So we have a 3-meter wide hallway and a 2-meter wide hallway. Theta is marked, okay. AB is a thin metal tube which must be kept horizontal and cannot be bent as it moves around the corner from one corridor to the other. So we have this pole that we're trying to navigate or move around the corner. Okay, so they're going to kind of guide us through this because otherwise it'd be fairly difficult to do. So let's be thankful that they are guiding us through this. Show that the length AB is given by capital L equals 3 over cosine theta plus 2 over sine theta. That seems a little daunting maybe, but if we just draw an auxiliary line here, perpendicular to the wall, and then draw another one here, perpendicular to the wall, we can use our good friend right triangle trigonometry. And let's see, this is parallel to this, therefore this angle right here must also be theta, okay? Or I'm sorry, this is parallel to this, so we have corresponding angles, my bad. All right, so now what are we going to do, okay? Well, I'm gonna go ahead and label this from here to right here. I'm gonna label this a length of A, and from here to here, I'm gonna label it a length of B. And I'm just gonna write here that AB is equal to little a plus little b. Why am I doing that? Well, I'm going to be using some right triangle trigonometry, and if I've made two little triangles, so I needed to label the two hypotenuses, I guess, hypotenuse I. We'll have to look that up. I don't know. So I can represent their lengths with the right triangle trigonometry. So, how do I figure that out? Well, I need A, I have an angle, and I have a side that is adjacent. So I think that you would agree with me, using right triangle trigonometry, that A is equal to 3 over cosine theta. How did I do that? Because cosine theta equals adjacent 3 over hypotenuse, A. And then solving for A, we get 3 over cosine theta. Similarly with B, theta, opposite is 2, hypotenuse is B. So sine theta equals 2 over B. And solving for B, we get B equals 2 sine theta. Nope, not 2 sine theta, 2 over sine theta. Sorry about that. Okay, so therefore, AB equals A plus B, which we called L, so I should have put L here. L equals AB equals A plus B. So L clearly is equal to 3 over cosine theta plus 2 over sine theta. Okay, so we have knocked out part A. Check! All right. Show that the derivative of the function L with respect to theta is equal to 0 when theta is equal to the tangent, or when theta is approximately equal to 41.1 degrees. Okay, so we have to take the derivative, set it equal to 0, and find theta. Okay, so I'm going to rewrite L. I'll do this one in pink just because. Okay. I have to take the derivative of this function, and I don't want to use the quotient rule for this one. I think it'd be easier just to write them as two individual terms and take the derivative. So I'm going to rewrite this as L equals 3 cosine -1 theta, bringing cosine theta up from the denominator, plus 2 sine negative 1 theta. Okay? So if I take the derivative of that, I'm going to use the chain rule. The outside function is the exponent negative 1. So this becomes negative 3 cosine negative 2 theta. Let's see, multiplied by negative sine theta. The derivative of cosine theta is equal to negative sine theta. Okay. Let's see, so this will be using the exponent first, minus 2 sine negative 2 theta, subtracting 1 using the power rule, and then the derivative of sine theta is cosine theta. Okay, so there we have it. So what does that equal? That equals a negative times a negative is a positive, so that's going to equal 3 sine theta over cosine squared theta. Okay, taking this and moving it to the denominator, minus 2 cosine theta over sine squared theta. Okay, and now we have to figure out when this is equal to 0. So I am going to make it one rational expression, so I can just figure out what the numerator, when the numerator is equal to 0. That will be a lot easier. So my common denominator is going to be sine squared theta times cosine squared theta. Okay, just the product of these two denominators. So I'm going to multiply this guy, both numerator and denominator, by sine squared theta. And I'm going to multiply this guy by cosine squared theta, both numerator and denominator. And in doing that, I get 3 sine cubed theta minus 2 cosine cubed theta all over sine squared theta cosine squared theta. So the only way, oh sine, not plus, it's cosine squared theta. So the only way a fraction is equal to 0 is when the numerator is equal to 0. So now I have to solve this. Okay, I have to say, okay, I got to set my numerator equal to 0. 3 sine cubed theta minus 2 cosine cubed theta is equal to 0. Remember, I'm looking for tangent, so that tells me I need to get a sine divided by a cosine situation going here. So I'm going to move cosine theta over to the right side, cosine cubed theta. I'm going to divide everything by 2 and then everything by sine cubed theta, and I would get, cosine cubed theta, and then everything by 3, because I want to get sine over cosine for tangent. So I would end up with sine cubed theta over cosine cubed theta equals 2 over 3. Well, sine over cosine is tangent, so sine cubed over cosine cubed is tangent cubed theta. So tangent cubed theta equals 2/3. And to solve for that, I take the cube root, and I get tangent theta is equal to the cube root of 2/3. Ding, 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 looky there, right here. Okay, here's the cube root of 2/3, but I have to solve for theta. So on my calculator, which I'm not going to show you right now, I would say theta is equal to the inverse tan of the cube root of 2/3, and I will tell you that that is approximately equal to 41.1 degrees. Okay, so we have done part B, right? So that means that the derivative is equal to 0 when theta is equal to 41.1 degrees. Okay, so find L when theta equals the tan -1 of cube root of 2/3 and comment on the significance of this. Okay, we'll find L. Okay, Well, what's L equal to? Well, L is equal to 3 over cosine theta plus 2 over sine theta. So L would be equal to 3 over cos 41.1 degrees plus 2 over sine 41.1 degrees. And you crank that into your calculator and you get L approximately equal to 7.02. And we are in meters, I believe. Yes, we are. We're in meters, so that's 7.02 meters. Okay, and it says comment on the significance of this. Okay, so let's think about this. We took derivative and we set it equal to 0. Yes, and so we found a turning point, and that was at 41.1 degrees. Okay, so I'm doing a sign diagram here, SIGN. And if I took, like, let's say 40 degrees, and I found it using my calculator, and I found the value of it replacing theta with 41.1 or 40 degrees, it would come out negative. And if I replace theta with something greater than 41.1 degrees, it would come out positive. This indicates that we have a local minimum here. Okay? And when we have that minimum, we can use it to find the length when theta is with that local minimum. And what that gives us is the greatest length of rod able to be horizontally carried around the corner. In other words, we could not have a rod greater than 7.02 meters long because this is the minimum angle that we could have. Okay, and with that minimum angle comes the greatest length that the rod could be. All right, so a little bit of a complicated problem. Hopefully you followed it. If not, write down your questions or put them in haiku, and we will take care of them in class. That is it for optimization examples. We shall see you next time.